Video, we're going to be talking about how to find the surface area of a pyramid and then eventually how to find the surface area of a cone as well. First off, let's start with that pyramid. Pyramids can come in a few different shapes, but they're usually named based on whatever their base shape is. So for example, this one, all sides are equal on its base, so that would be a square-based pyramid. Also, if all sides are equal on a base, we call that a regular pyramid. Just like a regular polygon has all equal sides, a regular pyramid will have bases that have all equal sides. So the examples that we'll see today will be regular pyramids. That'll kind of help with our math. In surface area, sometimes it's possible to unfold a shape and make what's called a net, which is essentially kind of what this is, although we're missing the base here. But the problem is that when we get into more complicated shapes like the pyramid and the cone, that net can be less helpful because sometimes we're just not given information enough to fill out the net. And especially we'll see that in the cone. But I want to start off just by saying that with this pyramid because I want to emphasize just using the formulas instead in this video. In order to find the lateral surface area, which would be the area of these triangular faces around the top of the pyramid, we can find their areas by taking half of the perimeter of the base and multiplying by what's called the slant height. And the slant height is a little bit different than the pyramid's height. The pyramid's height would be a line that would come from what's called the apex here, straight down and hit the middle of the base, and it would be perpendicular to that base. That's not what we're given when we're given the slant height. The slant height is actually the height of the triangles that are on these side faces or the lateral faces. So the slant height would be the height of the lateral face. To find the total surface area, we'll take that lateral area and then we'll combine it with our base area, and that will give us our total surface area. We'll do 3 different examples because they can get a little bit harder depending on the information given. In this first example, we're given the slant height and we're given a base length, and we're told that they're regular pyramids. So if I'm given one length of my base, I know that all of the lengths on my base are the same. So all of the lengths here are 6. I can find that base perimeter by just multiplying one side length by 4, or I could add 6 plus 6 plus 6 plus 6. So the base perimeter is 24. The slant height, which is given to us, the height of that lateral face, is 11. So we have everything we need to find that lateral area. We're going to take half the perimeter times our slant height, and we get 132. Now we can find the base area. Since we know it's a square base, we could do our side length squared. So 6 squared is 36. We can take that lateral area and that base area, combine them together, and get our total surface area. So the surface area of this pyramid is 168 square inches. In the next couple examples, we'll see how it gets a little bit trickier if we're not given that slant height. If we're not given the slant height, we should be given enough information to find it. For example, here in this pyramid, we're given this pyramid height, and that creates, or we can draw to create, a right triangle here. This side length of our right triangle, since it's in the middle of my base here, is going to be half of the side length. So given 24 the height, and then figuring out that half of our side length is 10 right here, we now know 2 out of 3 sides in this right triangle, and we can use Pythagorean theorem to find that third side. So knowing that we want to find the hypotenuse in a right triangle, we can take the square of the 2 legs, combine those, and then square root that value, and that gives us our hypotenuse length of 26. There are also some special right triangles that are used often. One of those is called a 5, 12, 13, and then you can have any scale of that ratio. So this is actually a 5, 12, 13 just scaled up twice as big. So a side length of 5 doubled would be 10, a side length of 12 doubled would be 24, and that hypotenuse of 13 doubled would give us 26. So knowing those special right triangles can sometimes save you the use of the Pythagorean theorem, but we can use that Pythagorean theorem to prove it if we forget. So now we know our slant height is 26. We know our base length is 20. So we can figure out everything we need for this surface area. Let's find the perimeter of the base. We have a side length of 20 4 times, so let's do 20 times 4 and get 80 for our base perimeter. And we now have our slant height, so we can find that lateral area, which is half of our base perimeter times the slant height, and we get 1040. We can find the base area. Since we know its length, then we know it's a square. We're just going to square that side length. 20 squared is 400. Let's take that lateral area and that base area and combine them and get 1,440 square meters for the surface area of this pyramid. Lastly, what happens if we no longer have a square-based pyramid and we have a triangular-based pyramid? It's still a regular pyramid, meaning that the side lengths of the base are all the same, so this is actually an equilateral triangle on the base. We have enough information to find that base perimeter. Since all the lengths are the same, we could just triple our side length of 4 and get our base perimeter of 12. We're also given the slant height in this example, so we can find our lateral area. Take half the base perimeter and multiply by your slant height. So the lateral area is 42. Now the base area is where it gets tricky in a triangular prism. Because this triangle is equilateral, we don't know the height of that triangle. These side lengths are not perpendicular. A base and a height have to be perpendicular. So we have a base. We could use any of these base lengths of 4, but we have to find the height of this triangle on the bottom here. This side of the pyramid is actually overlapping what I would use to draw my height there. So if we just ignore this top half up here and just look at the triangle right here, we have side lengths of 4 and this altitude or height of our triangle right here that we drew being perpendicular to one of the bases. In an equilateral triangle, the altitude or the height is going to bisect one of our bases. So instead of having a full length of 4, we could have 2 equal lengths of 2 on each side. And then now we can see this right triangle. We know the hypotenuse is 4, and we know one of its legs is 2, and the height being the other leg is missing. We got to find it. So we're going to use Pythagorean theorem again, and then we'll get that height, and we can find that base area. So knowing that we are missing a leg, one cheat to the Pythagorean theorem is that we can take the hypotenuse squared and subtract that leg squared from it, and then square root it. If that's jumping too many steps, then go ahead and start with the Pythagorean theorem where you have 2 squared plus x squared equals 4 squared, and then solve it algebraically. You should get the same answer. We get about 3.464, and because we're getting a decimal value that I need to use in additional steps, I don't want to round it too early here. I want to keep at least 3 decimal places. That'll ensure that I'm staying more accurate than just rounding right now and using that rounded value. All right, so we got the height. We can find the area of our base triangle here. We're going to do our base length of 4 times our height. And with triangle area, we take our base times our height and we cut that in half. And so the base area of the bottom triangle there is about 6.928. Again, I'm using 3 decimal places here because I got to use this value in another step. We got our lateral area, we got our base area. Let's combine them, and that'll be our total surface area. We could round that to the 10th and make it about 48.9 square centimeters. So there's a few examples with pyramids, some square-based and triangular-based. If you know that slant height and a side length of your base, then you have everything you need to find the surface area. Let's talk about the surface area of a cone. Here is the net. So if I was to unwrap a cone, I would get this shape here. And this is why using the net of a cone is often not very helpful, because in order to find the sector area here, representing the top lateral area of our cone, we would need to know an angle measure here for our sector. And oftentimes when you're dealing with a cone, they're not going to give you the angle measure of the sector here. So we really have to rely on some other formulas rather than using the net. So to find the lateral surface area, we're going to take the radius of our circle here, or the base, and we're going to multiply that by our slant height. Again, that slanted height on the outside of the cone, and then multiply that by pi. That will represent our lateral area. So that's not including the circle's area. That's just the triangular cone up top. If you've ever had a paper cup then this is exactly what we're finding. The amount of paper that would make that cup would be the lateral surface area. If it had a lid, then that would be the base area. So oftentimes with cones we don't have a lid, it's just an open top. But in the following examples we'll pretend like they have lids and we'll be able to find the total surface area. If we include that base circle area, then we can find the total surface area, just add it to our lateral area. So to find the area of a circle, we got r squared times pi, that's our base. We have our lateral area, radius times slant height times pi. And another way that we can write this, because we have two terms here that share some common terms, we could factor and rewrite. Because these two terms both have an r in it, we could factor out an r, but that leaves an r here. And because they both have pi, we could factor a pi out. And since we factor an r and a pi out here, that leaves an L in that last spot. So here's just a factored form. It's kind of a little bit easier to use than maybe this, but you have your choice whether you want to use this one or this one. Let's do some practice. In this left example here, we're given the height of the cone, and we're given the radius, and we're not given the slant height. So just like in our pyramid, we can use some right triangle math. We have a right triangle here. We know the two legs, and we're looking for the hypotenuse representing that slant height. So again, we could take the square of our two legs, combine them, and square root it to get our hypotenuse, and we get 20. Another cheat here is that this is also another special right triangle. It's called a 3, 4, 5. That would be the ratio of the sides. 5 being the hypotenuse, 3 and 4 being the legs. And this is just quadrupled. It's a multiple of 4 here. So if we take 3 times 4, we get 12. 4 times 4 is 16. And that length of 5 times 4 gives us a length of 20 in this bigger right triangle. It's a little bit of a cheat there if you know your special right triangles. Now that we know the slant height and we know the radius, we can figure out the surface area here. The lateral area is going to be that slant height times our radius times pi. So we get 240 pi. And if I was asked to find just the lateral area using a decimal value instead, I could take this value in terms of pi and convert it using either 3.14 or pressing the pi button on our calculator. We're going to find the total surface area, so we're going to include that base area here. The area of the circle is going to be our radius squared times pi. So 12 squared times pi gives us 144 pi. And the reason why I left it in terms of pi is because I want to know what the total surface area is, and I can combine these two pieces. And if they're like terms, then I can actually combine them. So since they're both in terms of pi, let's put them together and get an answer in terms of pi. We get 384 times pi. And now my last step would be to use the pi button, or 3.14. In this case, we want to use the pi button. And we'll be able to round it and approximate it in decimal form. So 384 times pi is about 1,206.4 square centimeters. So there's doing it in pieces, finding the lateral area and the base area. Although we do have this one formula where we can put it all together in one step here. And so I did that right here just to show you that this is much faster and much less steps than doing it in pieces here, and we get the exact same answer. All right, on this example on the right here, this time we're given the slant height, and we're given the height of the cone, even though it didn't copy very well. That's what this was supposed to represent. So we're missing the radius. So again, we have this right triangle shape, and we can use that to our advantage to solve for the radius. Since we have the hypotenuse and we're missing the leg, I'm going to use that shortcut where I take the square of the hypotenuse and subtract the square of the leg, and I get the other leg value when I do that. So we know the other leg, or the radius, is 15. And actually this is another 3, 4, 5 special right triangle, except it's just been multiplied by 5, a scale of 5. So you got 3 times 5 is 15, 4 times 5 is 20, and then 5 times 5 is 25. Although Pythagorean theorem just proved that for us anyways. Now that we know the radius and the slant height, we can find our surface areas. We take the lateral area, our radius times our slant height times pi, and get 375 pi. Let's find the base area of the circle, radius squared times pi, so 225 pi. Combine those two terms to get our total surface area. Combining those terms in getting 600 pi for our total surface area. And then using the pi button, doing 600 times pi, we get 1,885-ish square centimeters. Again, doing it in pieces, or I showed you what it looks like if we were to just use this one formula to do it all at once, making it much faster. We get the exact same answer. All right, so there are surface areas of cones. You got your formulas right here to use. Good luck finding surface area of pyramids and cones.